Welcome to qnawire.
Right, so we've got our diagram, our free body diagram at the left here. There's the force of the spring, kx, and there's the frictional force, mu mg, and then there's that constant force that we're applying, which is 82 newtons. So we know it's just a conservation of energy problem. So off over here to the right, we have the work that we put into it is going to be equal to the kinetic energy that it has after we push it, right? So we just gotta calculate that work, and we know that work is the force you apply times the distance you push it. So when that force that we're pushing it with isn't constant, we have an integral. So we've got our integral here over the net force applied to the block, which gives us our total work. Now this middle term here, this is interesting. When you integrate this, in that integral, you're going to get 1/2 kx squared, which is the potential energy of the spring. So that is not something that we're going to need for the kinetic energy. So let's just cross that out and don't look at it anymore. It's going to fall out in the end, right? And that's an assumption that we're making because the work is really equal to the kinetic energy plus the potential energy. Okay, so we're going to cross that out and we're going to cross this out and just make it easier for us. Okay, so we do that integration and we see that our total work is 53 joules, and this is just the amount of work that goes directly into kinetic energy. So then we know that the kinetic energy is also equal to this 53 joules, and we can use that to find the velocity. So we use the same equation linking velocity and kinetic energy that we've always used, where the mass, again, is 4 kilograms. And we come out with this velocity when it's compressed, 0.8 meters, is 5.14 meters per second. So now we go into the B part, where we need to find the acceleration at that point in time. Now, the acceleration is always just the force divided by the mass. So this just comes from F equals ma, like it always has. And this is the net force at that point in space divided by the mass. So this here on top is the net force, and so we have to use this equation again. But in this case, we cannot take out this part, right? Because the spring is acting on it too. It's acting on the block too. So when we have to take the net force, we take 82 minus k times the compression at that point, minus mu mg. That's the net force. And then we divide it over this m, right, which is the mass of the block. We come out with a final answer. After you do that, should be negative 44.7 meters per second squared. We'll make a better 7. Okay. So this is a little bit counterintuitive because you're pushing it and you have a negative acceleration. And that just means that what's going on is it's not as fast a moment in the future as it was in the past, right? So it's slowing down.